So today I want to talk about section 5.6, which is inverse trig functions. So this is kind of, not in the theme of what we've been talking about thus far. This has nothing necessarily to do with exponential functions or natural log functions, but it is in the theme in that it's about inverses. And to some extent, this section is about tying up loose ends. So here, for the trigonometric functions, what we would like to do is define inverses and then, do some calculus with them, figure out their derivatives and integrals. So the first thing to keep in mind is if you think about the graph of, for example, the sine function, it's, that last part was unfortunate. It's not one-to-one. So here, first and foremost, what we do is we restrict the domain of the sine function to minus pi over 2 to pi over 2. So the sine function would go forever, but we restrict the domain to minus pi over 2 to pi over 2. That's just kind of arbitrary. Someone decided to go minus pi over 2 to pi over 2. That's the standard construction. And now the function becomes one-to-one. And so now if it passes the horizontal line test, it's one-to-one. We can reflect it about the diagonal and create the inverse. And so basically I took, this graph of the sine function that's been restricted, and we've reflected it about the diagonal to now create the inverse. And so here's the definition of the inverse. And it's defined in an indirect way. It's defined based on how an inverse is supposed to behave. So here we define the inverse of sine of x to be what we call the arcsine of x. And here's the definition. So first, here's the notation where y equals, and then there's this sine of x with this little -1 between the sine and the x. So this should be pronounced as the inverse of sine of x or the arcsine of x. And what's the definition? It's very sneaky. They say y equals the arcsine of x if and only if sine of y equals x. So the inverse is defined in terms of the function sine. And now here's what I want you to practice. How do I get from this equation that's here on the left-hand side, how do I get to this equation here on the right-hand side? So if we apply sine to both sides of this equation on the left, I get sine of y, which is what I have here, equals sine of the inverse of sine of x. And so sine and arcsine, since their inverses cancel out, and the sine of arcsine gives you back this x. And again, how do we get from the equation on the right-hand side to the left-hand side? I need to apply the arcsine, the inverse of sine, to both sides of the equation. Apply it. So here, arcsine of sine of y just gives me back y. And then arcsine of x is exactly what we have on this other side of the equation here on the left. So it's really important that you get this idea of going back and forth. And we'll do this a bunch of times today, okay? Because this is essentially how we work with these functions. Given y equal to arcsine of x, typically we'll write it as sine of y equal to x and then do math. The other thing I want to mention to not, let these things confuse you. First, this thing, x between -1 and 1. Remember that the domain of the inverse is the range of the original function. And for our sine function, you remember sine is bounded above and below by -1. So this domain, this domain statement is coming from, what's the range of the inverse here? The range of the inverse is -1 to 1. So the domain, the range of sine is -1 to 1. So the domain of the inverse of sine is -1 to 1. And the other thing here that I want you to look at is here it says y has to be between minus pi over 2 and pi over 2. So this y right here is the same as this y right here. Now you remember, the range of the inverse is the domain of the original function. So if I look at the original function, here we restricted the domain from minus pi over 2 to pi over 2. that's where this restriction is coming from. The domain restriction of sine becomes the range of the inverse of sine. So if we think about the geometry, it kind of all makes sense here, the domains and ranges and stuff like that. And so, of course, at the end of the day, if you just know the graph, that solves a lot of issues. So here's the graph. So if you know the graph, that solves a lot of issues. Or certainly if you know how to derive the graph starting from sine, that also, can be helpful depending on how you like to learn things. Some comments here, some alternate notation. Instead of writing sine to the -1, some books also use arc sine. Be very careful here. The sine to the -1 is not a reciprocal. When the -1 is between the sine and the parentheses x, it's an inverse. The way I would write a reciprocal, I would write this as sine parentheses x, and then put the -1 out here. Or put parentheses around the whole thing and put a -1. But a -1 in between the sine and of x, that typically means the inverse function. Certainly it does in our textbook. So we do the same trick basically with the cosine function now. Instead of restricting it from -π/2 to π/2, cosine wouldn't be 1-to-1 from -π/2 to π/2, right? Because of its shape. But if we restrict it from 0 to pi, then this thing passes the horizontal line test. It's 1-to-1. And so now I can take the graph, flip it around the diagonal, and essentially, create the inverse. And so that's what happens here. We're able to create the inverse of cosine, or what's known as the arc cosine of x. And again, we define it using the inverse. It's a very indirect definition. I say why, so remember first and foremost, this function, the inverse function, is an input-output machine. So for the input x, we say the output is y if and only if cosine of y equals x. If and only if for the cosine function, if the input is y, the output is x. We just reverse that relationship. And I'm gonna, just mention this again. How do we get from the equation on the left to the equation on the right? What I want to do is apply cosine to both sides of this equation. Then cosine of y gives me the cosine of y part here. Cosine of the arc cosine of x is going to be x because cosine and arc cosine are inverses and they undo each other. That's basically just the property of inverses. And again, the domain and range stuff. So here, the domain of the arc cosine will be the range of cosine. The range of cosine is -1-to-1. And here, the range of arc cosine will be the domain of cosine, the restricted domain of cosine. And here we restricted the domain to be 0 to pi. And so that's why this y term, that's the range of arc cosine, is 0 to pi. And you can see on the graph here, here's the range. And the domain of the original function became the range of the inverse. You can see they flip-flopped. As before, we have alternate notation. We can write arc cosine. And again, I caution you, this is not the reciprocal, it's the inverse of cosine or arc cosine. It's not 1/cosine. And we do this for the tangent function as well. With regards to the tangent function, we look at the tangent between -π/2 and π/2. And so here you'll notice the range of the tangent function is all reals. So the domain of the inverse will be all reals. And here, if we reflect it across the diagonal, we get our inverse, the graph of the inverse. And you can see the domain is all reals. And here, the tangent is restricted between -π/2 and π/2 in its domain. So it's inverse, the inverse tangent now, its range is restricted between -π/2 and π/2. It's that flip-flop relationship between the function and its inverse, right? The domain of one becomes the range of the other and vice versa. So here's the arc tangent. We say y equals arctan of x if and only if tan of y equals x. And again, just to really, bug you about this, if I apply tangent on both sides, that gets me to tan y equals x. If I apply arctan to both sides of the equation here on the right side, arctan of tan of y gives me y, and arctan of x gives me this arctan of x. So we can go back and forth here from the equation on the left-hand side to the equation on the right. And you should think about that and kind of be comfortable with that. And again, the range here of the inverse is the domain of this restricted tangent, minus pi over 2 to pi over 2. And the domain, is the range of tangent, which is minus infinity to infinity. So here we do have some limit properties. So the graph is really important to know when you do limit problems. So here, based on the graph, you can see the limit as x goes to negative infinity is minus pi over 2, the limit of arctan, and the limit of arctan as x goes to plus infinity is pi over 2, and arctan is a bounded function that it's between minus pi over 2 and pi over 2. So these are all nice properties of arctangent that we should know. And knowing the graph gives you all that information. Arctangent is really important. It shows up a lot in Calc 2. So yeah, we have the arctan alternate notation, and here again, this is not a reciprocal. And here we talked about the inverses of sine, cosine, and tangent, and those are the ones that'll be emphasized for the exam. But of course, we can find the inverses of all 6 of the trig functions, and I'll show you that in a second. And so you might see all 6 of the inverse trig functions in your homework, and so that's fine for the homework. But as I said, for the exam, we'll focus on arcsine, arccosine, and arctan. So here, let me show you how we work with the arcsine or any inverse function. So here we want to find the exact value of arcsine of root 3 over 2. So the first thing I want you to realize is for the regular sine function, the input is an angle, the output is a number. So for the inverse sine, the arcsine, the input is a number, the output will be an angle. So here, arcsine of root 3 over 2, I'm looking for some kind of angle answer. Anyway, here's the standard way we work with inverses. We reverse the equation. If you give me y equal to f inverse of x, I'll apply f to both sides and write it as f of y equal to x, and then do the necessary math. So here, let me first name this thing. Let me call arcsine of root 3 over 2, let me name it y. I say here, let y equal the thing I'm trying to find. And, I know the range of this arcsine will be minus pi over 2 to pi over 2. That was the domain restriction to make sine 1 to 1. That'll come up in a second here. So now here's this reversing technique that I was talking about. I go from y equals arcsine of root 3 over 2 to sine of y equals root 3 over 2, and I convert this to a trigonometry problem. How did I do that? I'm applying sine to both sides of the equation. Here you get sine of y equals sine of the inverse sine of root 3 over 2. Sine of the inverse sine is just root 3 over 2. And here, remember, y is an angle. If you want to think of this as theta, sine of theta equals root 3 over 2, you can. But this is now just a trig problem. I'm now trying to figure out for which angle theta is the y coordinate root 3 over 2. So if you think about your unit circle, it's going to be 60 degrees. The bigger angle gives us the higher y value there. And so here it's pi over 3. And here there's only one answer. That's why we restricted. The whole point of restricting the sign is so that it's 1-to-1, so that when you find its inverse, you have a legitimate function, which means you only get from one input, one output. So here we only should get one answer for the y. And so the only answer that's between minus pi over 2 and pi over 2 that works is pi over 3. And remember, you can think of this region minus pi over 2 to pi over 2. We can think of it as this region. Now I'm thinking in terms of angles. So minus pi over 2 to pi over 2. For your root 3 over 2, there's only one angle, is 60 degrees. Yeah, so the trick is to rewrite the problem, convert it to a trigonometry problem, and now you're just back to doing trigonometry. You know, it's not even calculus, you know what I mean? But of course, we need to know our unit circle, and Trig's definitely not easy. So unit circle and boning up on that stuff never hurts. Here, let's do a limit problem. So now we're starting to do some calculus. There's 2 limit problems here. The limit is x goes to 0, arctan of e to the x, and the limit is x goes to infinity of arctan of ln of x. And look here, I wrote arctan in 2 different ways just to irritate you. These are the same function written in 2 different notations. I'm trying to give you your money's worth, people. So here, let's do each limit separately. You know, for arctan and e to the x, I would think about the graphs. And if you think about the graph, you know, we could conclude they're both continuous. And now go back all the way to chapter 1. The composition of continuous functions is again continuous. And now you say, so what? What does that have to do with limits? Remember, continuity is a limit property. Continuity means we can find the limit just by plugging in the number. That's what continuity means. And here, because we are dealing with continuous functions, I just plug in the number for x. E to the 0 is 1. And now I have to figure out arctan of 1. You know, so very quickly, here, set this equal to y and convert the equation. If you take the tangent of both sides, I get 1 equals tangent of y. And now this is a trigonometry problem. So now I'm thinking, what angle, for which angle is the tangent of that, you know, equal to 1? So tangent of pi over 4 is 1. So here I'm able to conclude the limit is pi over 4. And here I wrote out those calculations again explicitly where I convert it. So here I call arctan, I name it, I call it y, and then I reverse the problem by taking the tangent of both sides. I take the tangent of y, gives me this term here. Tangent of arctan just gives me 1. And now I'm solving a trigonometry problem. And I'm, you know, here, y equals arctan. So y has to be in the range of arctan. So I know y has to be between minus pi over 2 and pi over 2. Think about the graph of arctan. It's bound between pi over 2 and minus pi over 2. So here I'm only solving tan of y equals 1 for the answer that's between minus pi over 2 and pi over 2. And so the only answer is pi over 4 here. So yeah, converting this to a trig problem is really, you know, a standard technique here for working with these inverse trig functions. For the second limit, I'm just analyzing this piece by piece using continuity again. You know, here there's this inside function ln of x. So I want to ask myself, when x goes to infinity, what happens to ln of x? Well, as x goes to infinity, we know from the graph of the natural log that ln of x blows up to infinity. So then I want to ask myself, okay, for the arctan function, if the inside of the arctan function blows up to infinity, what happens to arctan? And so again, if you look at the graph, arctan will go to pi over 2 if x goes to infinity. So now we can put all of this together. So here I take the limit. The limit of arctan of ln of x. So here, as x goes to infinity, the ln of x part, this part, blows up. And when the argument of arctan blows up, this whole thing goes to pi over 2. So just by kind of analyzing the behavior and looking at the graphs, I conclude the limit here of arctan of ln of x as x goes to infinity equals pi over 2. And as I mentioned, the graphs are super important. So here's the graph for natural log, and then the graph of arctan. You know, it's bounded above by pi over 2 and bounded below by negative pi over 2. And so knowing the graphs really helps to figure out the limits, and you can do it piece by piece to see what's happening. So here's one more problem. So you know, you might see something like this in the homework. It says simplify the expression, the tangent of arc sine of x. So right away, I want you to stop and first think about the arc sine of x. Here, this is the opposite of sine. The input will be a number, the output will be an angle. So it makes sense to ask about the tangent of arc sine of x. We're asking for the tangent of an angle. That makes sense. So now let's actually kind of figure this out. As before, name the inverse. I'm going to call arc sine of x y. Just let y equal arc sine of x. That's one of the most fundamental steps to working with these inverse functions, is to name it and then reverse the problem. So once I say y equals arc sine of x, I can rewrite that as sine of y equals x. And remember what I did? I applied sine to both sides. So I get sine of y equals sine of the sine inverse of x, which is just x. Now, I interpret the sine as in terms of trigonometry. I write x as x over 1. And remember, the sine is opposite over hypotenuse. So I'm able to build a triangle. So here, y is the angle. Remember, y equals arc sine, and the range here, we expect arc sine to spit out an angle. Y is the angle. The side opposite the angle should be x, and the hypotenuse should be 1. Then sine of y equals x over 1, or sine of y equals x. So now, remember, this arc sine is this angle y right here. So now I want the tangent of y. And if I know two of the sides, then using Pythagoras, I can find the third side. And here it's a little more complicated. And so let me show you when we find the third side. So here's my Pythagorean theorem. L here is the number 1. So I'm calling, sorry, is x. So I'm calling this right here L. And h here is our hypotenuse, which is 1. Okay, so W would be down here. This is, so if I solve for W, because it's squared, if you actually do the math, you get plus minus. Here I wrote just plus because that's actually the correct answer. I'll show you in a second, but let me show you how I know it's the positive root. So now we can take the tangent of arc sine, it's the tangent of that angle, and the tangent's opposite over adjacent. Here the opposite is x, and the adjacent, as I mentioned, is plus minus square root of 1 minus x squared. And as I mentioned, there's two possible roots in the denominator, so I need to get rid of one of them. So there's still one piece of information we never used, and that's x is greater than 0. You know, how does that help? Well, if we look at the graph of arc sine of x, okay, and the arc sine of x graph looks something like this. And here it goes all the way up to pi over 2. If x is greater than 0, here's x. If x is greater than 0, that means we're in this section of the graph, which means y, which is the arc sine, so remember this is y will be between 0 and pi over 2. Because when x is greater than 0, the range of arc sine is between 0 and pi over 2. Think about that in terms of angles. In terms of angles, it's what I'm saying is y is in the first quadrant. Y is between 0 and pi over 2. If x is positive, the arc sine will be positive, which means y will be between 0 and pi over 2, which means this angle here, arc sine of x, or this angle y, is in the first quadrant. In the first quadrant, tangent is positive. I don't know if you did this in calculus. We have this thing, all students take calculus, and it tells us which trig functions are positive where. And in this first quadrant, all the trig functions are positive. So here the tangent here of y, since it's in the first quadrant, cannot be negative. So here I'm going to take the positive root. So you should think about that. It's not difficult. It's just a lot of annoying trigonometry and just keeping track of the graphs and the range and input and output. Okay. So remember here, arc sine is an angle. That's really one very important thing to remember. Here, when I say y equals arc sine, y is an angle. And now x being greater than 0 forces y to be between 0 and pi over 2. And so tangent has to be positive. So we end up picking the positive root. So I'll let you think about that. And the one thing I really, really want to emphasize is this, where we reverse the equation. That technique we used again here. That we'll use again and again. So by the way, as I said, we can find the inverses of the other 3 trig functions. And the definition is in the usual way. We define the inverse in terms of the original functions. So y is the arc cosecant of x if and only if cosecant of y equals x. And then there are domain restrictions on the original functions to make them one-to-one. These you do not need to know for the final exam, but they may show up in your homework. Your slides might have different graphs here. So originally I used pictures of the graphs, and then I ended up actually rendering or plotting the graphs. So these are actual plots of the graphs. I didn't want to give you pictures. I wanted to give you the real deal. And so I'll repost these. And so here are all the graphs all together in all their glory. You should, be familiar with these top 3, especially the arctan one, as I said, is especially important in Calc 2. So let's find a derivative since this is a calculus class. So for the derivative of arc sine of x, we're going to do the same trick. I'm going to reverse the equation and then try to take the derivative. So here, starting with y equal to arc sine of x, hit both sides with sine. Then I get sine of y equals sine of the inverse of sine of x, or sine of y equals x. Now we're going to differentiate, but be very careful. Y here is a function of x. So when we're looking at sine of y, what we have is a composition of functions of x. I have sine of f of x, where y is the function of x. So when I take the derivative of sine of y, I need a chain rule. The derivative of the outside is going to be cosine y times the derivative of the inside. The inside is y, and the derivative of y is just y prime. Of course, on the other side, the derivative of x with respect to x is just 1. So here's your derivative of the outside times your derivative of the inside. There's y prime is your derivative of the inside. Now we're trying to solve for y prime. So let me isolate y prime. So here I see y prime equals 1 over cosine y. We've technically found the derivative, but we would really like the answer in terms of the variable x. And here, sine of y equals x. So if I can write cosine of y in terms of x, then maybe I can get back to the x variable. So now we use some trig identities. I know sine squared plus cosine squared equals 1. And so you can solve for cosine squared. Sine squared plus cosine squared equals 1. So we can solve that cosine of y is plus minus root 1 minus sine squared of y. And here, look, we technically have 2 roots. And I need to find a way to eliminate one of these roots. So here, if I go back and look at y, remember y is the range of the inverse, so it's the domain of the restricted sine function. So y is between minus pi over 2 and pi over 2. That's the 4th and 1st quadrant. So here, minus pi over 2 to pi over 2. And if you think all students take calculus, in the 4th quadrant and the 1st quadrant, cosine's always positive. So here I want the positive root. And finally, replace sine of y with x. And so now I get an answer in terms of x. And so here's our derivative. You should learn the derivative of arc sine. You should memorize that. You should also pay very close attention to this technique where we reverse the equation and then do the math that we need to. In this case, implicit differentiation. Let's find the derivative of arctan. So we're going to use the same technique. If y equals arctan, if I take the tangent of both sides, I get tangent of y equals the tangent of arctan of x, and tangent and arctan are inverses, so I just get tangent of y equals x. Now, tangent of y is a composition of functions of x. Remember, y is a function of x. So do a chain rule. The derivative of tangent, the outside part, is secant squared. The derivative of y, which is the inside part, is y prime. Solve for y prime. Y prime equals secant squared. Technically, we've found the derivative, but what we would really like is a formula of the derivative in terms of the variable x. And here, tangent y equals x. So if I can write secant squared in terms of tangent, then, I can convert it all to x's. So now if you go back to this identity, I don't know if you remember this identity, but if you, starting from sine squared over cosine squared equals 1, if you divide both sides by cosine squared, then I get sine squared over cosine squared is tangent squared plus cosine squared over cosine squared is 1. So tangent squared plus 1 equals 1 over cosine squared. I get tangent squared plus 1 equals secant squared. And so here, the secant squared, I've replaced with 1 plus tangent squared. And that's coming from, you can derive that directly from sine squared plus cosine squared. As I said, if you have sine squared plus cosine squared equals 1, just divide both sides by cosine squared. And finally here, tangent of y, we can replace with x, right? So remember here, x equals tangent of y. So finally, I get the derivative of arctan of x is 1 over 1 plus x squared. And you should memorize this. Of course, you should also know this technique here where we reverse the equation, right? That's also very important. So when I say y equals arctan and switching it to tangent of y equal to x, that's a very important technique that we should also, appreciate here. So colorful. All right, folks. So now we get here are the derivatives of all 6 of the inverse trig functions. It's a lot in this one section. It's literally Calc 1 all over again. Here's a whole bunch of new functions. Here's the domain, here's the range, here's the graph, here are the derivatives, here are the antiderivatives. Remember, for the final, we're going to emphasize these 3 functions, arcsine, arccosine, arctan. And if you look at arccosine and arcsine, their derivatives are almost identical. They only differ by a minus sign. Anyway, so you should learn all these derivatives for the example. Of course, in the homework, you might see, all 6 of these. And that's fair game for the homework. In the homework, you can just look up the table to see what the derivative is. And so now, for example, on the exam, you might see some traditional differential equation problems, derivative problems, Calc 1 problems, but using these new functions. Here's a traditional derivative problem where the functions involved are all quote unquote new functions. Here, what you should recognize first and foremost is a composition. I have ln of x inside of the arctan. So for compositions, we should use a chain rule. And so for my chain rule, I need a derivative of the outside, the derivative of the arctan part. Derivative of arctan of x is 1 over 1 plus x squared. So here for the derivative outside is going to be 1 over 1 plus ln of x, the whole thing squared. Because this is a chain rule. It's the derivative of the outside evaluated at this inside function. Now I do derivative of the inside. So times the derivative of ln of x, which is 1 over x. And so now, we can, I just put the 2 denominators together. And there's my derivative of arctan of ln of x using a chain rule. And this would be, a pretty typical type of problem to see on the final. So now that we know derivatives, we also know antiderivatives. And for antiderivatives, the main 2 antiderivative formulas that we're emphasizing for the exam is the antiderivative of 1 over positive square root of 1 minus x squared dx, which is arcsine of x, and the antiderivative of 1 over 1 plus x squared dx, which is arctangent of x. And remember what this notation means. This notation says the derivative of arctan of x plus c is 1 over 1 plus x squared. And we showed that using, on the previous slide, by reversing the equation and using implicit differentiation. And again here, this is saying that the derivative of arcsine of x is 1 over the positive square root of 1 minus x squared, which we also verified by reversing the equation and using implicit differentiation. So these antiderivative formulas have been proven. We now just have to kind of fold it in with all the other problems that we're using, that we do, and all the other antiderivative formulas that we have. So take a look at this problem. It's the antiderivative e to the x over e to the 2x plus 1 dx. This is a tricky problem, and we kind of have to learn from this example. So here, the trick is to let u equal e to the x. And I know that doesn't seem obvious, but the reason I'm doing that is because the e to the 2x, I can write as e to the x squared. And so if I let u equal e to the x, then du is ex dx, which is good because in the numerator, I have an ex dx. And so that's what's a little tricky about this problem. This ex in the numerator, I'm not going to replace with u. I'm going to put the ex in the numerator with the dx and replace it with du. However, this e to the 2x, I'm going to write it as e to the x squared. And here, I'm going to replace this e to the x with u. In the numerator here, this e to the dx becomes du. And so here's our transformed integral. It looks like 1 plus, 1 over 1 plus u squared du. And we know now the antiderivative of that is arctan of u. Then I replace u with e to the x. And of course, we can always verify by taking a derivative. So yeah, it's a little tricky problem, but now that you've seen it, we kind of have to, make it just kind of part of the examples that we keep memorized in the back of our mind for u substitution problems. And this is a very common trick when e to the x is involved, where we save one of the e to the x's and combine it with dx to make it our du. And then all the other e to the x's are converted into u's. And so that's just something to remember here, that the reserving one e to the x for the dx to make that a du. So the next two examples I want to show you, mainly because there's a shortcut formula in your textbook, and I want to explain where the shortcut formula is coming from. So this is not a difficult problem, but it does use some algebra, and it's generally a good review of the math techniques in general. So at the end here, this is a really great kind of general review. So here it's the integral of dx over x squared plus 4. And anytime we have a sum of squares in the denominator, one thing to try and see is if we can't, make this look like antiderivative of 1 over 1 plus u squared. So that's what I'm going to try here. So my first issue is I have a 4 here instead of a 1. Well, there's no problem. What I can do is I can factor out a 4. So from x squared plus 4 in the denominator, I factor out a 4. So I have 4 times x squared divided by 4 plus 1. And so there's the plus 1 in the denominator that I was looking for. This 4 that's right here, I'm going to pull it out and write it in the front as 1/4. And I'll just multiply the answer at the end by 1/4. And this x squared over 4, I want to write it as a single variable squared. So I'm going to write this as x over 2, the whole thing squared. So take a look. Starting from x squared plus 4, I factor out the 4, pull that out. That's where this 1/4 comes from. The x squared over 4, I write it as x over 2, the whole thing squared, because I want this to look like a single symbol squared, blah squared. So here, blah is x over 2. Now, I'm going to replace the x over 2 with u. So use the substitution, let u equal x over 2. Then du is dx over 2. I don't have the over 2 part, but that's okay if my du is off by a constant. I can multiply on the outside by a 2 and divide by a 2 on the inside, or I could just solve for dx. Here I did the multiplying dividing thing. So here I've divided dx by 2, but I've also multiplied on the outside by 2. So what happens now, dx over 2 becomes du. This x over 2 in here, this becomes a u. And the 2/4 that's out in front, I can simplify the 2/4 and write that as a 1/2. So when I convert the integral, I get 1/2 integral of 1 over 1 plus u squared du. And now we know the antiderivative of 1 over 1 plus u squared du, that antiderivative is arctan. And my last, copy down the 1/2. My last step is to replace the u, since the original problem is in terms of the variable x, and here u is equal to x over 2. So the generic formula now in general is if you have the integral of 1 over x squared plus a squared, where that's a constant. So in this case, we have x squared plus 2 squared. So here the a is 2. So the general rule is the antiderivative is 1 over a arctan of x over a plus c. And here's an example of that formula where a was 2. And so if you do this exact same u substitution, instead of having a 4 here, if you had an a squared here and use this substitution x over a instead of x over 2, you'd get this shortcut formula here that's in the book. To me, it's not necessarily obvious that the antiderivative of this thing on the left-hand side just equals this, So that's why I wanted to explicitly show you the math for where that comes from. So as I said, the math here on this slide is not difficult. There's very little calculus, in fact. It's a majority of it is just algebra, just trying to manipulate it to make it look right. And once we get it to look the way we want, which is right here, this is the only place where any calculus happens. I just apply the anti-differentiation rule. That's the only place where there's any calculus. Everything else is just, algebraic manipulation, just making it look different. So this next example is a similar type of example. There's a formula in the textbook, but it's, unless you see the derivation, it's not obvious where it comes from. So the generic formula in the textbook, it's the integral of dx over positive square root of a squared minus x squared. And they say that'll always equal, I believe it's the arc sine of x over a. So here I've picked an example where a is 3. So think of this as integral dx over square root of 3 squared minus x squared. And let me show you how this goes. Again, because we have a square root of a difference of squares, we're going to try and see if we can't make this look like, an antiderivative that'll give us an arc sine. So in the denominator, first thing I do is factor out a 9. And remember, this is still under the square root, okay? So factor out a 9. I get 9 times quantity 1 minus x squared over 9. Now I use the fact that the square root of a product, square root of a times b, radical a times b is the same as radical a times radical b. So what I do is I separate this. I write this as radical 9, which is a 3, and I factor out the 1/3. And that's where this 1/3 comes from. That's actually 1 over radical 9. And then the other term here is the square root of 1 minus x squared over 9, which is right here. The square root of 1 minus, and I wrote x squared over 9 as x over 3 quantity squared, because I wanted to write it as a single symbol squared. So this is all just algebra. We haven't done anything fancy. Factor out a 9, break up the root. Square root of 9 is 3, so that's where the 1/3 comes from. And here's square root of 1 minus x squared over 9, which I write as x over 3 squared. So now we use the substitution, let u equal x over 3. I want this x over 3 to be a single symbol. So I'm going to call it U. And then, of course, we have our du. And here, actually, we have the dx over 3. I'd factored out the 1/3. I could put the 1/3 back in and we'd have dx over 3. But here, I just multiplied and divided by the 3. It doesn't matter. It's still the same effect. Here, I divided by 3, multiplied by 3. And there's the 1/3 that was hanging around there anyway. The 3 over 3 will disappear. Here, dx over 3 will become du. And in here, x over 3 will become a u. So now I get integral 1 over root 1 minus u squared du. And this is the only part now where there's any calculus. We now know the antiderivative of this function is arcsine from the work we did. And now replace the u with what we originally substituted for. And now here's the more generic formula that I mentioned that the book gives. And so, without any explanation, it's not necessarily obvious why this would be true. And so I wanted to do one example to show you all the sort of the intricate calculations that get you there. And as I said, these calculations on this page should be okay because it's all algebraic manipulation. We're just trying to get it to look a certain way. And once we get that look, then we apply our known antiderivative formula. So this ends the discussion of section 5.6, and I'm going to stop right here.